I always start with my data here, 5 data points. I have to build graph on top of it, which are simplicial complex. Here is simplicial complex X. Having my simplicial complex, I can start defining the notion of a chain complex Cn of X, which correspond to the n simplices, n in 0, 1, 2, up to some natural numbers. For example, when I want to compute the C0 of S, I'm computing the vector space with basis the 0 simplices. The 0 simplices are V, W, X, Y, Z. I can also compute C2 of X, which is a vector space with the basis the 2 simplices. Here I have only 1, 2 simplex K. That's why C2 of X is Z K. Z2 of K. Z. Since I don't have any high dimensional simplices when n is greater or equal for Cn of X will be 0 when n is greater or equal 3. Let me point out that here we are working with the field of coefficient Z2 because it's more practical when we are doing topological data analysis. Having the simplicial complex, I can now compute the n homology, which correspond to the n cycle divided by the n boundaries. For example, the 1 homology is a 1 cycle divided by the 1 boundaries. Cycles here are in the sense of graph theory. So the 1 cycles here are A plus B plus C. That's why I have this. And D plus E plus F. That's why I have this second cycle. Now, when I divide by 1 boundaries, I have only here a boundary of a 2 simplex. That means the boundary of K. The boundary of K is just this A plus B plus C. Simplifying my relations, I will have D plus E plus F as the base of the first homology group. We are explaining that there is a hole here on my simplicial complex. Therefore, we can see that the first homology is just giving me the shape of my simplicial complex, since the Betti number 1 is 1. Hence, the simplicial complex X has a 1-dimensional hole. Now that we know already the notion of simplicial complex and homology, this is the workflow or the pipeline for you to know the shape of your data. I always start with data, which I point in some Euclidean space. I compute an algebraic object on top of it. From the algebraic object, I can compute the homology that will help me to know the shape of my data. For example, we computed the first homology here, and we have seen that there were a hole here. Having now the shape of data, I can do some statistical analysis, or I can fit it. I can fit some machine learning algorithm with it to do some artificial intelligence task. In this pipeline, the more difficult part is moving from data to algebraic object. But there are several algorithms like check complex, Victorius-Rips complex, alpha complex, Witten complex, cubical complex. But here I will limit myself on the explanation of the check complex. We always start with data here corresponding to 1, 2, 3, 4, 5, 6, 7 data points. We build poles around each point with a certain radius R. When 2 balls intersect, we build a 1 simplex O and H. When 3 balls intersect, we build a 2 simplex. More generally, when K plus 1 balls intersect, we build a K-simplex. This is nice, but you might ask yourself, how do we choose R? In fact, we don't choose any value of radio. We consider all possible value of radia, and we keep track of the evolution of the homology associated to each simplicial complex for a given radius. That means that this pipeline was not totally correct. Let us rectify it. I start with my data, and as I am building ball around each point with a certain value of radio, I will get many algebraic objects. Therefore, data, the pipeline is data and then algebraic or sequence, family or sequence of algebraic objects. And for a given algebraic object, I will have to compute the homology, which give me the shape of my data. And I will just consider the shape that persists the most as the radio R is evolving. This is an introduction of the notion of persistent homology. Thank you for watching this video, and bye-bye.